Okay. So what is second harmonic generation imaging? So second harmonic generation imaging is basically is a frequency doubling effect. So when it's a coherent nonlinear optical process in which two resonant photons at a same frequency is annihilated or combined to form a third frequency or third photon with double the frequency. So it's basically a frequency doubling effect. Um, and and right after the invention of the laser, this so early on, this Franken, what he did is he used the intense source of laser uh, on a silica, okay, quartz, okay, quartz, which we all know is silica. And when he analyzed then he saw mostly the red light, which is 694 nanometer, the fundamental frequency, but also he saw this higher order on nonlinear effects, okay, where he saw this also this weak UV photons, 347, exactly at double the frequency or half the wavelength. Okay, so early on, this was in early 1960s, and later on it became very popular, where you can convert the visible light into the UV light with applications in laser. And some of the early crystals were used where this potassium dihydrogen phosphate, KDP, lithium niobate, and ammonium dihydrogen phosphate and urea were known to give you a very strong second harmonic response. Okay, and when this electric field, okay, interacts with the material, okay, it interacts with what? Electrons. Material is composed of electrons, so you have this electric field interacting with the material, induces a second order polarization, which is proportional to or is equal to this the number of molecules that gives you the second harmonic response, and the second order polarizability or first order hyperpolarizability, which describes the charge oscillation, this oscillating dipole in the medium in presence of a strong electric field, and also the electric field of the incoming photon. Okay, and one important point I want to make here is the SHG is forbidden in bulk. Okay, where you have this randomly oriented dipole or oscillating dipoles, where you have when you have a random orientations, the net electric field gets cancelled due to the destructive interferences, and you can see that it is forbidden, and this hyperpolarizability becomes zero because of the cancellation of dipole moments. But when you have ordered geometry, that's where the SHG is very bright, okay, because you have a coherent summation or amplification of the signal through these electric fields that constructively interfere, gives you a strong SHG response. Okay, so it's allowed in a ordered structure. So that's basically also represents non-centrosymmetric versus centrosymmetric. So when you have a non-centrosymmetric systems, that's where you have a strong SHG response. So it was well known in the community that collagen gives you a very bright SHG signal. Okay, and so we wanted to. So in LSU, they have nice veterinary school also, and very good interdisciplinary collaborations. So we wanted we wanted to look at this myocardial infraction model in mouse hearts, which is basically myocardial infraction is a terminology used to represent heart attack. Okay, and of course we all know that the healthcare industry spends billions of dollars in this heart attack related disease. So we wanted to look at this heart attack model that where what we do is this, our collaborator, he does a surgical ligation of left coronary artery to induce a heart attack because of this reduced blood flow to the heart and leading to the heart attack. And what you can do is basically extract the tissues at different time points, okay, in a living mouse, and then you can basically characterize them, especially for the collagen, because in cardiac fibrosis, it is well known that there is a secretion of extracellular matrix proteins, particularly collagen. So we wanted to basically monitor this time-dependent collagen distribution in infracted mouse hearts. And the second objective also was to look at not only collagen isoform, but collagen per se, but also look at collagen types, different types, okay, particularly type 1 and type 3, which is found in heart. And recent research should focus on or should move in this direction, where you can use this microendoscopy, okay, where you can basically capture the weak SHG scattering from collagen, and so that you can do a real-time monitoring, which has of course implications in heart transplant related diagnostics, as well as you can basically look at other disease models also, which involves the the collagen isoform distribution, or there is a secretion of collagen proteins, and also analysis, image analysis, right? You want to, of course, extract the information so that you can interpret the data, and basically early detection of heart attack is a key area of research in this. How early and precisely you can detect the heart attack. So I just would like to give you a very brief introduction to collagen before I particularly collagen types. So collagen is a protein, okay, and collagen, the nonlinear response comes from these amide bonds, okay. So it's like a tropocollagen unit. It's like around 300 kilodalton protein, has about 280 nanometers diameter, okay. It's a triple helix, and diameter 280 nanometer in length, and 1.5 nanometer in diameter. And this amide bonds with polarizable electrons, okay, gives you the nonlinear SHG response in collagen. And in collagen, you have like a lot of these amino acids, 1,000 amino acids. So the tight alignment of these peptide bonds in this fibrillar geometry leads to, again, SHG, right? You have this ordering of these amide bonds, where you can have a coherent amplification of the signal, which gives you a strong SHG response. And they can form fibers about microns long, and few hundred nanometers in diameters. And what we not only detected collagen, but there are around 25 types of collagen, but the fibrillar collagens are type 1, type 2, and type 3, which basically varies in that these alpha units, alpha helix units. So collagen type 1 gives you a strong SHG, has 2 alpha 1, 1 alpha 2, which and whereas type 3 collagen, which is also found in heart, is 3 alpha 1 chains, okay, but gives you a weak SHG. And here this is basically related to this charge distribution, as well as this pitch angle, which is basically a helical coil. This is a protein with respect to the linear axis of protein, and this basically distinguishes these alpha chains. So we wanted to study this collagen types in mouse hearts, and here I'm showing you some results on this time-dependent progression of cardiac fibrosis. So the top panel shows you the label-free, so no labeling, no fluorescence labeling, endogenous or like intrinsic signal from the collagen, as well as this red. So here the red channel basically is representing the endogenous autofluorescence coming from 2-photon fluorescence, and the green channel represents the SHG channel. Okay, so time-dependent progression of cardiac fibrosis was monitored over 4 weeks, and you can see that as with increasing time points, we see that after you induce the heart attack, you have this this thinning of left ventricle as well as dilation. Okay, in the left ventricle, you can see the diameter increasing, as well as you have increased collagen deposition. Okay, and this is shown here in this graph here, plotted with different time points. You can see that nearly an exponential growth before it levels off. Okay, it plateaus after like 2 to 3 weeks, and we saw around 20 times, more than order of magnitude increase in collagen deposition after 2 weeks after myocardial infarction, after you induce a myocardial infarction. And this is a very simple, also you can do bright field microscopy where you need to stain it using picroseries dye, which binds to the collagen protein. And you can simply by using transmitted light microscopy, also you can look at this collagen. And also you can do polarized light microscopy to look at the birefringence from collagen also. And you can see here the SHG scattering from collagen around 430 nanometer in this infracted mouse heart, also where you have this thinning of the left ventricle region. You have significant collagen deposition. You can see around 430 nanometers, very sharp peak coming from collagen. And as I mentioned, we not only wanted to detect collagen, but also resolve this collagen isoforms or collagen types. So for this, we designed an experiment where we use this antibody labeled dyes. Okay. So for example, there is a collagen 1 antibodies that will specifically bind to the collagen type 1 protein. Okay. And you can have collagen type 3 antibodies that will bind to the collagen type 3 proteins. Okay, so what we did is we did a 1 photon fluorescence, or you can say a linear fluorescence, to detect this collagen channel, collagen 1 in a fluorescence channel, as well as simultaneous acquisition of multi-photon SHG, together in a sequentially. We basically collect the SHG as well as a 1 photon fluorescence from this dye labeled antibodies, and then we do a co-localization analysis. As you can see that when you have no fluorescence labeling, you don't have a detectable fluorescence, but when we of course do this 28-day MI induced sample, and this is basically a left ventricle region. You can see that the SHG channel, fluorescence channel, and you can merge them, and we do a co-localization analysis using this imaging softwares from Leica, and these white pseudo-colored white region is showing you basically the co-localization pixels, okay, between the antibody labeled collagen 1 and SHG, and we see that increased co-localization in the case of collagen 1, and much less co-localization with respect to collagen 3. Okay, and this is basically also shown in this plot here, co-localization rate, and our results showed that collagen 3 is secreted, is expressed first in mouse hearts at early time points, and then as infract progresses, the more mature collagen type 1 is predominantly found in mouse hearts. Okay, is regulated. Okay, is upregulated in this. And here, what I also showed is, through another series of experiments where we also looked at this fluorescence analysis, fluorescence imaging of these tissues, and we showed that this SHG channel is basically is due to the collagen type 1. Okay, so we analyze the fluorescence channel as well as the SHG channel, and we show that the time dependent progression of SHG and collagen, SHG and SHG follows the collagen 1 using fluorescence. Okay, so what we showed is basically here is there's a type 1 collagen which gives you a strong SHG signal, is a primarily is giving us the SHG response.